Welcome to this walkthrough of LeetCode problem number 426, Convert Binary Search Tree to Sorted Doubly Linked List. In this session, we'll explore how to transform a binary search tree into a circular, sorted doubly linked list using efficient algorithms. Let's dive in. In this problem, we are given the root of a binary search tree, or BST, and our objective is to transform the tree into a sorted circular doubly linked list. The transformation must be done in place, which means we'll use the existing left and right pointers of the tree nodes as the previous and next pointers in the doubly linked list. Importantly, the order of the nodes in the final doubly linked list must follow the in-order traversal of the BST. Additionally, since the doubly linked list is circular, the next pointer of the last node in the list should connect back to the first node, and the previous pointer of the first node should connect to the last node. This ensures that the list forms a complete loop in both directions. Now, in terms of input and output, the input we'll work with is the root of the binary search tree. The root is a reference to the topmost node of the tree, and each node in the BST has three main properties: a value, a reference to a left child node, and a reference to a right child node. In the output, we'll return a reference to the head of the resulting doubly linked list. Each node in the doubly linked list will maintain the same value as the original BST node, and its left and right pointers will represent the previous and next nodes in the list, respectively. Let's look at an example to clarify this further. If the input binary search tree has the structure shown, with 4 as the root, 2 and 5 as its children, and 1 and 3 as the children of 2, the output would be a circular doubly linked list in the order 1, 2, 3, 4, 5. This order comes from the in-order traversal of the BST, which visits the nodes in sorted order. In the doubly linked list, each node's left pointer connects to the previous node, and its right pointer connects to the next node. For instance, node 1's left points to node 5, and its right points to node 2. Similarly, node 5's right points back to node 1, forming the circular link. In another example, if the binary search tree has 2 as the root, with 1 as its left child and 3 as its right child, the resulting doubly linked list will have the nodes in the order 1, 2, 3. Again, this follows the in-order traversal of the BST. The circular property is maintained, so node 1's left points to node 3, and its right points to node 2. Node 3's right points back to node 1, completing the loop. This demonstrates that the algorithm handles smaller trees effectively while maintaining the correct order and circular structure. For a very simple case, if the binary search tree consists of only one node, such as a tree with the root value 1, the resulting doubly linked list will have just one node as well. Since it's circular, the node will point to itself for both the left and right pointers. This means node 1's left and right both refer back to itself, forming a circular structure with just one element. This is the base case where the tree contains the minimum possible number of nodes. Finally, let's consider some edge cases. First, if the input binary search tree is empty, meaning the root is null, the output should also be null because there are no nodes to convert. For a single node tree, the output will be a circular doubly linked list where the single node points to itself. Another interesting edge case is when the tree is skewed, either entirely to the left or entirely to the right, resembling a linked list. Regardless of how unbalanced the tree is, the algorithm must still produce a doubly linked list in sorted order while maintaining efficiency. These constraints ensure the solution is robust and handles all possible scenarios efficiently. To solve the problem of converting a binary search tree into a sorted doubly linked list, we evaluated several approaches. The first method we considered was the brute force approach, which involves performing an in-order traversal of the BST. This traversal naturally provides the nodes in sorted order. Once we have the nodes or their values stored in an array, we can manually construct the doubly linked list by iterating through the sorted array and linking the nodes together. While this approach is straightforward, it does require additional space to temporarily store the nodes or their values, which violates the in-place constraint of the problem. Moreover, although the time complexity is O(n), due to traversal and list construction, the extra memory usage makes this method less optimal for our needs. An optimized approach involves constructing the doubly linked list directly during an in-place in-order traversal of the BST. The key idea here is to leverage the natural order of nodes visited in an in-order traversal to link them as we go. By maintaining two pointers, one for the previously visited node and another for the head of the list, we can efficiently update the pointers of the current node to form the doubly linked list. Specifically, for each node, we set its left pointer to the previous node and update the previous node's right pointer to the current node. Finally, we close the circular doubly linked list by linking the head and tail nodes. This approach is highly efficient, with a time complexity of O, n, and a space complexity of O, h, where h is the height of the tree due to the recursion stack. It also adheres to the in-place requirement, making it an attractive solution. Another viable option is to use an iterative approach to perform the in-order traversal. This method avoids recursion by explicitly using a stack to simulate the traversal. As with the recursive approach, we maintain two pointers, one for the previously visited node and one for the head of the list. During the traversal, nodes are linked in the same way, with the current node's left pointer set to the previous node and the previous node's right pointer updated to the current node. At the end of the traversal, the head and tail are linked to complete the circular doubly linked list. The iterative approach has the same time complexity, O, n, and space complexity, O, h, as the recursive method. However, it avoids the recursion stack, making it more robust for BSTs with significant depth, where recursion could lead to stack overflow. The strategy we selected as the primary solution is the optimized recursive in-order traversal. This method aligns perfectly with the requirements of the problem. Since the in-order traversal naturally visits nodes in sorted order, it allows us to efficiently construct the doubly linked list in place. The elegance of this approach lies in its simplicity and efficiency. It achieves O, n, time complexity and O, h, space complexity, which are optimal for this problem. Additionally, the recursive implementation is clean and easy to follow, making it highly readable. The key insight that led to this approach was recognizing that the in-order traversal directly produces the sorted order needed for the doubly linked list. By linking nodes during traversal, we eliminated the need for additional data structures or post-processing, resulting in a solution that is both efficient and elegant. When comparing the recursive and iterative in-order traversal methods, the recursive approach stands out for its simplicity and readability. However, the iterative method has the advantage of avoiding the recursion stack, making it a safer choice for trees with large depths. On the other hand, the brute force approach, while conceptually straightforward, is less suitable because it relies on extra space to store node values temporarily, violating the in-place constraint. By contrast, the recursive in-order traversal strikes the ideal balance between clarity, efficiency, and adherence to constraints. It avoids unnecessary memory usage and achieves optimal performance, which is why it was ultimately chosen as our preferred solution. In this problem, we are tasked with converting a binary search tree into a sorted doubly linked list that is also circular. This means that the smallest node in the BST becomes the head of the DLL, and the largest node becomes the tail, with the tail pointing back to the head. To achieve this, we can leverage the in-order traversal of the BST since it naturally visits the nodes in sorted order. A doubly linked list has two pointers for each node, one pointing to the previous node and another pointing to the next. For the circular structure, the head's previous pointer will link to the tail, and the tail's next pointer will link back to the head. The base plan involves visiting the nodes using in-order traversal, modifying their left and right pointers to act as the previous and next pointers of the DLL, and maintaining references to the head and tail for circular linking at the end. To implement this, we define a recursive algorithm. First, we create a helper function called DFS node to perform the in-order traversal. A global pointer, previous, is used to track the previously visited node. For each node, we link its left pointer to previous and update the previous node's right pointer to the current node, effectively creating the DLL links. Then, we update previous to the current node before moving to the right subtree. The traversal continues recursively for the left and right subtrees, ensuring that the nodes are processed in sorted order. Once all nodes are linked, we use the head and tail references to complete the circular connections. Special cases include handling an empty tree, where we simply return null, and a single node tree, where we link the node to itself to form a valid circular DLL. Here's the pseudocode for the solution. We initialize two global variables, previous, which starts as none and tracks the last visited node, and head, which is set to the smallest node during traversal. The DFS function first checks if the node is null and returns if it is. For non-null nodes, it recursively processes the left subtree. When visiting the current node, if previous exists, we link its right pointer to the current node and the current node's left pointer to previous. If previous is null, it means we are visiting the smallest node, so we set head to the current node. After processing the current node, we update previous to it and then recursively process the right subtree. Finally, in the main function, after completing the DFS traversal, we make the DLL circular by linking the head's left pointer to previous and the tail's right pointer to the head. The head of the DLL is then returned as the result. The algorithm provides several key insights. First, the in-order traversal is crucial because it guarantees that the nodes are visited in sorted order, eliminating the need for additional sorting steps. This allows the algorithm to achieve a linear time complexity of O(n). Second, the use of global pointers simplifies the linking process. The previous pointer ensures that each node is correctly connected to the previous one, while the head pointer is set only once, at the smallest node, and remains constant throughout. Third, to make the list circular, we simply connect the head's left pointer to the tail and the tail's right pointer back to the head. The input tree is a binary search tree with standard left and right pointers, while the output is a doubly linked list where left and right act as the previous and next pointers, respectively, completing the transformation. The algorithm has an efficient time complexity of O(n), as each node in the BST is visited exactly once during the in-order traversal. The space complexity is O(h), where h is the height of the tree. This space is used by the recursive stack, which for a balanced BST is O log n, and for a skew tree is O(n). To optimize further, recursion can be replaced with an iterative traversal using an explicit stack to prevent stack overflow for very large trees. Additionally, edge cases such as single node or empty trees should be handled explicitly to ensure correctness. For example, with a single node tree, the algorithm must ensure the node is self-linked to form a valid circular DLL. Let's consider an example to better understand the execution flow. For the given input BST, the in-order traversal visits the nodes in the order 1, 2, 3, 4, and 5. As nodes are visited, they are sequentially linked to form the doubly linked list. 1 is linked to 2, 2 to 3, 3 to 4, and 4 to 5. Once all nodes are processed, the circular linking is applied. The smallest node, 1, has its left pointer updated to point to the largest node, 5, and the largest node, 5, has its right pointer updated to point back to the smallest node, 1. The resulting circular doubly linked list is 1, 2, 3, 4, 5, where the head and tail are connected to complete the circular structure. Here, we start by defining the structure of a node class, which represents the individual elements of the binary search tree. Each node has a value, a left pointer, and a right pointer. Then, we define the solution class, which contains the method tree to doubly list. This method is responsible for transforming the binary search tree into a sorted doubly linked list. We first handle the edge case where the tree is empty, in which case we simply return none. Next, we define a helper function called in_order_traversal to traverse the tree using in-order traversal, which ensures the nodes are visited in sorted order. This function uses two variables, first and last, which we declare as non-local to keep track of the head and the last processed node in the doubly linked list. Inside the traversal, we begin by recursively visiting the left subtree to process all smaller nodes first. Once we return from the left subtree, we handle the current node. If last is not null, it means we've already processed some nodes, so we link the last node's right pointer to the current node and the current node's left pointer to last. If last is null, it means this is the first node we're processing, so we set it as first, which will eventually be the head of the doubly linked list. Finally, we update last to point to the current node. After processing the current node, we then recursively visit the right subtree to handle all larger nodes. Once the in-order traversal is complete, we have processed all nodes in sorted order and linked them into a doubly linked list. At this point, first points to the smallest node, and last points to the largest node. To complete the transformation into a circular doubly linked list, we connect the first node's left pointer to last and the last node's right pointer to first. This ensures that the list is circular, with the smallest node linking back to the largest node and vice versa. Finally, we return first, which serves as the head of our circular doubly linked list. This head allows us to traverse the entire list in sorted order starting from the smallest element. To solve the problem of converting a binary search tree into a sorted doubly linked list, we start by defining the structure of a node. Each node in the binary search tree will have an integer value, as well as pointers to its left and right children. The constructor allows us to initialize a node with a specific value. Next, we define the main class, solution, which contains the key method, tree-to-doubly-list. This method takes the root of the binary search tree as input and handles a base case. If the tree is empty, we simply return null. After that, we declare two pointers, first and last, to keep track of the head and tail of the resulting doubly linked list as we build it. To traverse the tree in order and link nodes appropriately, we define a nested helper class with an in-order traversal method, which we'll use shortly to process the tree nodes. The in-order traversal begins by checking if the current node is null. If it is, we simply return, as there's nothing to process. Otherwise, we recursively traverse the left subtree first, which ensures that we visit all the smaller nodes before processing the current node. Once we return from the left subtree, we handle the current node. If the last pointer is not null, meaning we've already processed at least one node, we link the last node to the current node by setting last.right to the current node, and node.left back to last, establishing a bidirection link. If last is null, it means the current node is the smallest node we've encountered so far, so we set first to this node, marking it as the head of the doubly linked list. After processing the current node, we update last to point to it, and then we recursively visit the right subtree to process larger nodes. Once the in-order traversal is complete, the doubly linked list is almost fully constructed. The final step is to close the list to make it circular. We achieve this by connecting the first node, which is the smallest, to the last node, which is the largest. Specifically, we set first.left to last and last.right to first, forming the circular links. Finally, we return first as the head of the doubly linked list. At this point, the binary search tree has been successfully converted into a sorted, circular doubly linked list, where all nodes are linked in ascending order. To solve this problem, we start with a simple binary search tree. The tree has a root node of 4, with 2 as its left child and 5 as its right child. Node 2 further has 1 and 3 as its children, forming a balanced BST. The goal is to convert this tree into a sorted doubly linked list using an in-order traversal. Initially, we set first and last to none as placeholders to track the start and end of the DLL. Starting the traversal at the root, which is node 4, we first move to the left subtree. From node 4, we visit node 2, and then continue left until reaching node 1, the leftmost node in the tree. Since node 1 has no left child, it's time to process this node as part of the doubly linked list. When we process node 1, we check if first is none, which it is, indicating this is the first node we're adding to the list. We set first to node 1 and also set last to node 1, making it the most recently processed node. After this, we return to node 2. At node 2, we link last, which is currently node 1, to node 2. Specifically, we set 1.right to 2 and 2.left to 1, creating the first connection in the doubly linked list. We then update last to node 2 before visiting its right child, node 3. At node 3, we link last, now node 2, to node 3. This means 2.right is set to 3 and 3.left is set to 2. After updating last to node 3, we return to the root, node 4, to continue the process. At node 4, we link the last node, which is node 3, to the current node. This involves setting 3.right to 4 and 4.left to 3. We then update last to node 4 and move to the right subtree to process node 5. At node 5, we link last, now node 4, to node 5 by setting 4.right to 5 and 5.left to 4. With node 5 processed, the traversal is complete. To finalize the doubly linked list, we make it circular by connecting the ends. We set first.left to last, so node 1's left pointer references node 5, and last.right to first, so node 5's right pointer references node 1. The resulting doubly linked list is circular and sorted as follows: 1-2-3-4-5. Now, consider a simpler case where the binary search tree has only a single node, 1. We begin by initializing first and last to none and start the in-order traversal at node 1. Since this node has no left child, we process it directly. Again, we check if first is none, which it is, so we set first to node 1. We also set last to node 1, making it both the first and last node of the doubly linked list. Since node 1 has no right child either, the traversal ends here. To finalize the list, we connect the single node to itself, making it circular. This means first.left is set to last, so 1.left points to itself, and last.right is set to first, so 1.right also points to itself. The resulting doubly linked list is simply 1-1 in circular form. In the next example, the binary search tree has a degenerate or linked list shape. The root is node 1, which has a right child of 2, and node 2 has a right child of 3. We start by initializing first and last to none and begin the in-order traversal at node 1. Since node 1 has no left child, we process it as the first node in the list. We set first to node 1 and last to node 1. Then, we move to the right child, node 2. At node 2, we link last, which is node 1, to node 2 by setting 1.right to 2 and 2.left to 1. We update last to node 2 and proceed to its right child, node 3. At node 3, we link last, now node 2, to node 3 by setting 2.right to 3 and 3.left to 2. Finally, we update last to node 3. With node 3 processed, the traversal is complete. To close the doubly linked list and make it circular, we connect the ends. We set first.left to last, so node 1's left pointer references node 3, and last.right to first, so node 3's right pointer references node 1. The resulting doubly linked list is circular and sorted as follows: 1-2-3. This example demonstrates how the algorithm handles a tree that is already linear, transforming it into a circular doubly linked list while preserving the correct order. The time complexity of this solution is O(n), where n represents the number of nodes in the binary search tree. This comes from the fact that the algorithm performs an in-order traversal, visiting each node exactly once. Let's break this down mathematically. The recursive function in_order_traversal is called for each node, and at every step, we're performing constant work, such as linking the left and right pointers. Because there are n nodes in the tree, and each node is visited and processed once, the total work adds up to O(n). Additionally, after the traversal is complete, we make two final adjustments to close the circular doubly linked list. These operations, setting first.left to last and last.right to first, take constant time, O(1), and do not depend on the size of the tree. Combining these, the overall time complexity is O(n). The space complexity of the solution is O(h), where h is the height of the binary search tree. This is primarily due to the recursive nature of the algorithm, as each recursive call adds a new frame to the call stack. The depth of the recursion corresponds to the height of the BST. In the worst-case scenario, where the tree is completely skewed, meaning all nodes are either only left or only right children, the height of the tree is O(n), leading to a stack space usage of O(n). However, in the best case, with a perfectly balanced tree, the height is O log n, resulting in a stack space usage of O log n. Beyond the call stack, the algorithm uses only a constant amount of additional memory for variables like first, last, and the node pointers. Therefore, the total space complexity is O(h), where h is the height of the tree. To understand the efficiency of this approach, let's compare it to a brute force or naive solution. In a brute force method, we might first perform an in-order traversal to collect the nodes into a list or array. If the nodes aren't already sorted, we would then sort the list, which takes O(n) log n time. Finally, we would construct the doubly linked list, which requires another O(n). This results in a total time complexity of O(n) log n. Additionally, storing all nodes in a separate list would require O(n) space. In contrast, the optimized approach avoids intermediate storage and sorting altogether. By constructing the doubly linked list directly during the in-order traversal, we achieve a time complexity of O(n) and a space complexity of O(h), where h is the height of the tree. This direct, in-place construction makes the optimized solution significantly more efficient. Now, let's analyze the best, average, and worst-case scenarios. In the best case, where the BST is perfectly balanced, the height of the tree is O log n. The traversal still takes O(n), because every node is visited once, but the space complexity for the call stack is O log n. In the average case, with a reasonably balanced tree, the recursion depth remains close to O log n, and traversal still requires O(n), resulting in the same time and space complexities as the best case. However, in the worst case, where the tree is completely skewed, essentially forming a linked list-like structure, the height of the tree becomes O(n), leading to both time and space complexities of O(n). Regardless of the case, the in-order traversal ensures that each node is processed exactly once, performing constant work per node and maintaining the overall time complexity of O(n). Space usage, however, is dictated by the tree's height, which varies based on the tree's structure. To summarize, the optimized solution for converting a binary search tree into a sorted, circular doubly linked list achieves a time complexity of O(n), where n is the number of nodes, and a space complexity of O(h), where h is the height of the tree. This efficiency is due to the direct, in-place construction of the doubly linked list during the in-order traversal. Unlike brute force methods, which require additional storage and sorting, this approach minimizes both time and space usage, making it a highly effective solution for this problem. When working on this problem, there are several common mistakes to watch out for. First, forgetting to handle edge cases like an empty tree or a single node tree can lead to unexpected runtime errors. Always make sure to explicitly check for these scenarios to avoid issues. Another frequent mistake is breaking the doubly linked list structure by not correctly setting the prev_next and cur.previous pointers. If these connections are incomplete or incorrect, the resulting linked list will not function properly. Additionally, some solutions mistakenly extract all the values from the tree, sort them, and then reconstruct the linked list. While this approach might work, it violates the in-place conversion requirement and increases the space complexity to O(n). Lastly, using the wrong traversal order can lead to an unsorted list. Since this is a binary search tree, in-order traversal is essential to ensure the nodes are processed in sorted order. Pre-order or post-order traversal would not achieve the correct result here. Now, one particularly tricky issue is not handling the circularity of the doubly linked list properly. The problem specifies that the list should be circular, so the head and tail nodes need to be connected. Forgetting this step will result in an incomplete solution that fails to pass all test cases. From an interview perspective, this problem is an excellent test of pattern recognition, as it combines tree traversal with linked list manipulation, two skills that are frequently assessed in technical interviews. Mastering in-order traversal is especially critical here. The optimal solution achieves O(n) time complexity and O(h) space complexity, where h is the height of the tree, due to the recursion stack. Alternatively, iterative methods can reduce the space complexity to O(1), though they may be a bit more complex to implement. When discussing your solution, it's important to highlight trade-offs. For example, the in-place approach is more efficient, but you could also mention why extract and reconstruct is less optimal. Finally, always clarify the problem's requirements, especially whether the doubly linked list should be circular, as this detail can vary in different versions of the problem. There are also several related problems that you might encounter, each of which builds on similar concepts. For instance, LeetCode 114, flattened binary tree to linked list, also involves converting a tree into a linked structure, but here it's a singly linked list. LeetCode 156, binary tree upside down, requires another tree transformation that demands careful manipulation of pointers. Then there's LeetCode 897, increasing order search tree, which rearranges a binary search tree into a right-skewed tree, relying on similar traversal logic. Lastly, LeetCode 230, kth smallest element in a BST, focuses on extracting sorted elements using in-order traversal. As for alternative approaches, recursive in-order traversal is the most optimal for this problem, offering simplicity at the cost of O(h) space for the recursion stack. Alternatively, iterative in-order traversal reduces space to O(1), but can be slightly more complex to code. Extract and sort methods, while straightforward to implement, increase time complexity to O(n) log n, and violate the in-place requirement. Finally, Morris traversal achieves O(1) space complexity but involves a more intricate implementation, which can be harder to debug during an interview. Each of these approaches has its trade-offs, and understanding them will help you choose the best solution for a given scenario. To wrap up, we reviewed how to convert a BST into a sorted doubly linked list using in-order traversal. This problem highlights the importance of understanding both tree and linked list structures. Thanks for watching, and be sure to subscribe for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!